You're on the video.
Wait.
He said what's wrong?
Oh, I thought you said
Okay.
Okay. So let's look at it. Okay. Very first question was what type of function is to the right. The most common response I got was, actually let's talk about this. I got some people who said graphical here. I'm just going to kind of... So, is this function graphical? Say it again. The representation, be careful, language matters. The representation here is what? Graphical. Okay? The representation is graphical. We got to know the difference between representation and function. Because when I ask for one, I'm intending that one, right? So I'm glad I asked this question. Representation, that is graphical, but what type of function is it? Most common response was linear. Can someone give me an explanation for why they think it's linear? If you disagree, be ready to add on to or push back on that. So why would we think this is linear? Kristen, can we get our headphones out, please? Thank you.
because it's gonna get the same like rate.
It has the same rate? Okay. How do you know? Did you check it? We didn't check it? Okay. Anybody want to add on to who also agree it's linear? Going once, going twice. Alright, gotta get someone to push back on it then. Because 8 of us said it was linear, a whole bunch of us said graphical, but 8 of us said linear. Quite a few of us said exponential. It's a what?
Oh, no, I just repeated what you said.
Several of us said it was exponential. Man, this is a boring class, y'all. I can only do so much. What you got, Drake?
If it was linear, wouldn't it just go in straight lines?
Okay, if it was linear, what shape should we see on the graph? A line, right? So this is a good thing to learn from. Don't forget, this is a learning experience. That's why I'm not doing this for a grade, because we got to learn out of this. Literally, when we look at a linear function on the graph, what do we see? We see a... So think about that language, right? The language there matters. Linear means line, okay? Linear function is a line. So, now, it's not guaranteed to be an exponential, but it's definitely not linear. Is it exponential? And if so, how do we know? We finished dream job salary last week, didn't we? Yes? Well, so let's recap dream job salary. In the dream job salary, looked at the situation where, what was the bonus that I told y'all to do? How much? 200,000 signing bonus, right? And then plus, was it $60,000 a day? Okay. And so, when we made that table, right? That's a graph, not a table. When we made that table, day 0, how much money did this person have? So day 0, 200,000. And then day 1, 260,000. Day 2, 320. What's happening every single day?
It goes up.
Let's be more clear with that language. When you say it goes up, what do we mean by that? We are adding, right? So remember, we want to be clear with our language. We are repeatedly adding $60,000 per day. Does anyone remember what that looked like as an equation or as a graph? You good, Davis? By the way, just in case you weren't aware, we are going to get new groups immediately after this because I warned y'all on Friday, if we started switching cards, then we would get new groups. And I know not everyone, but a few of us chose to switch cards. So, repeatedly adding 60,000, what did that look like as an equation or as a graph? Should have had this in our notes, yeah? The notes, did we not get a chance to do, did we end just barely on the wrapping up of the task and not get notes in? Oh, tell me that stuff. Alright, cool. So let's recap this. I asked y'all to get those into your notes. I told y'all to take pictures, but I also understand. Does anyone remember what the equation would be then? For this one, for option 1.
60,000 X plus 200,000
So 60,000 what?
X.
Time, so like when you say days like this, plus 200,000?
Yeah.
Is that right? Now, we can write days out like that, and actually in statistics, that's usually what we would do. But what did a lot of us put here instead of the full word days? D. And don't forget, what's happening between that 60,000 and that D? They are being multiplied, right? Jaden, why are they being multiplied right there? Yes, right? Because they're right next to each other, we know they're being multiplied, but like, why does it need to be multiplied? Say that first part again. It's getting added constantly, right? Multiplication is repeated addition. Don't forget that. That's the fundamental piece here that a lot of people skip with, by the way, what form of an equation is this? Y equals mx plus b, right? We forget that m is being multiplied by x because it's constant repeated addition. That's what a linear function is at its core. And so when we graphed this function, and I'll show it again later, when we graphed this function, what type of function was this, or what do we see on the graph? It's a linear function, so what do we see? A line, there we go, okay. And does anyone remember what the y-intercept would be? We can both see it in the table, we can see it in the equation. See it in the table, we can see it in the equation. It's what?
200,000.
200,000. A y-intercept, so like if you think about your x values, here's my y-axis, this is where the y-intercept goes. What is the x value for the y-intercept? If here's -1, here's +1. What's the y value for the x-intercept? Or sorry, what is the x value for the y-intercept? 0. It's right in between the positives and the negatives. What's in between positive and negative, Malia? What's in between the positives and the negatives? 0, right? So when we talk about that y-intercept, we're talking about an x value of 0. Day 0, there's how much money? 200,000. Notice if I substitute 0 in here, what's 60,000 times 0? 0 plus 200,000 is 200,000. Don't forget, when we talk about a y-intercept, the foundational piece is knowing that x is equal to 0. Because if we let x equal 0 in the table, in the equation, or on the graph, it gives me all the same values, right? Remember we talked about the idea of equivalence. They may look different, but they're telling the same one. Story, right? So an input of 0, output is my y-intercept. Input of 0, output is my y-intercept. So we saw a y-intercept of 200,000. What was our rate of change? What was our slope?
60,000.
60,000, right? To 1, $60,000. Every one what? Day, right? That's my slope there. It has real contextual meaning. So, sorry for this giant recap to start today, but I definitely should have made sure. I think I ran out of time and didn't schedule that well. So, this is a linear function. What was the defining characteristic? We've talked about a lot of things here, but what defined this linear function? Say again. Constant repeated addition, or we call that a constant additive rate of change, right? In the table, we can literally see that repeated addition, right? What's my constant additive rate of change in the equation? The slope, right? That constant additive rate of change is my slope. Where do I see the constant repeated addition in the graph? In the slope, right? So slope is our constant additive rate of change. And that's what defines a linear function. Okay, so we'll look at that a little bit more later. So that's the backdrop to this first question. I'm going to give you a second to write down notes. If you need to add that into the linear versus exponential functions, either graphically or tabularly. So remember, there's the graphical side of linear, there's the tabular side of linear, there's the algebraic side of linear, but the foundation is they have constant additive rate of change. So this is 1/2 of what we discovered on Friday. By the way, Miles, while people are writing this down, is this a function? And how, if so, how do you know? Mm-hmm. Why? Just taking a shot in the dark?
Yeah, pretty much. I guess.
You talking about, did you just run?
Yeah, that equation or that function that we just did, that table, the graph. And so remember, the table, the graph, and the equation are all telling the same story, right? So either one, any of the ones that we look at, is this a function? Why? Okay, let's say I take out the word function, I just call it a linear relation. Is it a function? How? Why? Every input maps to one and only one output, right? Oh yeah, right? There's that definition of relation still there. And so the difference between that relation and that function, right? Each input maps to one and only one output. On day one, you're making how much money? Or you have how much total money? 260,000. Do you have any other options on that day? No, right? Each input maps to one and only one output. And we'll move after we finish going over this bell ringer, so don't pack up yet. So we're going to keep going over this information. All right. Questions about that linear function then? Feeling okay there? All right, we still got exponential, so that's why I'm saying don't pack up yet. So exponential, what was the situation for option 2? Was it a penny signing bonus? Okay, but then what, in the wording I said was on day 1 you get another penny for 2 cents. On day 2 you get 2 more pennies for a total of 4 cents. Day 3, 4 more pennies for a total of 8 cents. So what did we realize was happening every day? It was doubling, right? And so, what was the equation for this? What was it? 0.01 times 2 raised to the d. Why? And so like we can very clearly see what's the name of this type of function going to be. Or let's say it this way, why is this going to be called exponential? Not just because of the exponent. What about that exponent? Because the exponent is a variable. And we got to be clear about that. Because this will not be exponential. Anyone remember what this one will be? Ooh, we got some stuff to learn. All right? Regardless, none of these will be exponentials. They'll fall into the group of polynomials. There are different types of polynomials. So what makes this exponential? Because what's in the exponent? I need you to be clear about this. Because that's one of the biggest things that trips students up every year, is they want to call these exponentials, but they're not. To be an exponential, the variable has to be in the exponent. Because what defines an exponential function? Repeated multiplication. And Sarah, how do we show repeated multiplication in an equation? How do we, with an exponent, right? So constant, does anyone remember that fancy word I introduced at the end? Constant multiplicative, rate of change, defines an exponential. Boom. And so we saw that in the table. So days, money, day 0, 1 cent, day 1, 2 cents, day 2, 4, 8, etc. And I will remind you and point this out because I think it's going to be somewhat relevant to today. One of the things that Kelly made a comment on, she was like, I don't want to go all the way to day 30. Do you want to go all the way to day 30? No? Did some of us do that? Is that okay? But what can we see in this table early on so that we don't have to go to day 30? What do I see in this table? A pattern, a rate of change. Remember, tables are great for organizing and finding patterns, right? It can help us write the equation because I literally see where I'm starting. Once again, what am I going to call this 0.01? That 0.01 has a very important name that we just talked about earlier with linear. It's what, Jake? Why is it the y-intercept? Okay, so let's pick up that mathematical language. The x is, and an even better way to say that is, what's another word for an x? Is that my input or my output? Inputs, right? The y-intercept is when my input is 0, and so I know this is my y-intercept. So I'm starting at 0.01, and literally what's happening? We're repeatedly multiplying by 2. That's why some of y'all actually wrote this equation as 200,000, because that's where we're starting, and then we were repeatedly adding 60,000 a day, right? Same exact idea. It's where you're starting and then what you're repeatedly doing to it. It's a totally valid way to write that equation. Almost done. So, the formal equation is this. That's the exponential equation that we typically use. You can transform it, things like that, but what is this a going to be? That's my y-intercept, is where we are starting. Notice, and keep in mind, for every y-intercept, Davis, what do we know about every y-intercept that has and will ever exist? What's the one thing we've said so far for y-intercept? Like, this is when we have a y-intercept. Still on the board somewhere around me. Kyron? Ooh, guys, come on. Something we've been studying since middle school. It's boxed on the board. It's over my right shoulder. my left. My right.
X equals 0.
Oh, there we go. Woo! It's getting nervous, guys. All right. Hey, y-intercept. Dx is equal to 0. There we go. Okay. Even with this being all unknowns, this x is now what? 0. Anyone remember what b to the 0 is? It is. Do we know why? That was like I just accepted it once upon a time. Have you heard that it's 1? Yeah? Does anyone know why it's 1? We just kind of accepted it because someone told us, or the calculator told us it was 1? Okay. I'm going to take a little aside. You don't have to write this down, but I do want us to understand, because you can write this down, I will say. Understanding is a beautiful thing. Okay, so really quickly, what is, yeah, let's just start here. Let's use b. What is b to the first? Is what?
1. Or whatever the number is.
Okay, let's do 2 to the first then. What is 2 to the first?
2.
2. Okay, cool. What's 2 to the second? It's 4. Okay, but why is it 4? It's multiplied by 2. 2 to the third? But why would it be 6 or why would it be 8? What do we know we're doing? Now, one thing I want to emphasize, because what y'all are referring to is this exponent is what? An exponent showing repeated multiplication. There we go, okay. So, when I say that, I know I have 2 2's here, but I'm not multiplying by 2 2's. I'm starting with 2 and multiplying by 2. But what if I rewrite this as 1 times 2 times 2? Now, how many 2's am I actually multiplying by? 2 to the first means I am multiplying by 1 2. 2 to the third, I'm going to start with what number? And multiply by 3 2's. So if I have 2 to the 0, what am I still starting with? 1. And then multiplying by how many 2's? None. So I just don't have a 2 there. I'm not multiplying by 0, I'm just not multiplying by a 2. That's why 2 to the 0 is 1. And you can do this with all of these. Any base. 1 times 2b's. 1 times 3b's. And this will help explain, let's say I go backwards. Let's go to 2 to the negative 1. Anyone know what that is? It's what? Why don't you type 2 to the negative 1 in the calculator for me? It's what?
I think it's still 2.
Negative 2?
No, it's positive 2.
You think it's still positive 2? Why don't we type 2 to the negative 1 in the calculator?
It's a half.
It's a half. Did it give you 1 divided by 2? Huh. Interesting. So it's not negative, is it? It's not negative 1 times 2. 2 to the negative 2. 1/4? Or what's another way to write that based on what we were doing down here? 1 divided by what? Or I'm going to rewrite that 4 as 2 times 2, right? Notice when I go this direction, I am multiplying by 2. But what am I doing if I go backwards? I'm dividing by 2. This is why you'll never hear me say 1 over 2. You'll never hear me say 1 over 4. You'll hear me say 1 divided by 2, 1 divided by 4, because it's important to understand that that fraction bar is the inverse of multiplication. They are heavily related. So, dividing by 2 go this way. And so what's right in the middle? 2 to the 0, that's equal to 1. A positive exponent starts at 1 and then multiplies by that many, whatever the base is. A negative exponent, does a negative exponent make it negative?
No.
No. A negative exponent indicates repeated what? Division. So I should say whole exponents That's repeated multiplication. Negative integer exponents are repeated what? Division. You'll notice I am very intentional about saying whole or integers because let's say I have an exponent of 2.1, things get a little wonky. If I have an exponent of negative 2.5, things get a little bit wonky. There's more involved than just that. So I'm only talking about those integer exponents. You make sure we lodge that away 100%. So Shadidra, notice that blue is my linear function, right, a line. The red there is my exponential, 0.01 times 2 to the x. Do you still think that initial graph is linear? So this blue right here is my linear function from option 1. This red, 0.01 times 2 to the x, is the exponential. So remember that bell ringer I had you do, that original graph? Do you still think that's linear? What do you think it is now? Exponential. Did you know that this shape of a graph, and I would mark this down, the shape of this graph has a very important name. It's a type of curve, literally called an exponential curve. If you did not know that name, write it down because you will hear me say it. The shape of that curve is known as an exponential curve. And so remember I gave you that linear versus exponential, tabular versus graphical. This would be a good part to put under the graphical. Yes, ma'am. I do not, but if you need to run to the bathroom, you can. I don't think I do anymore. While some of y'all are finalizing those notes, I'm going to pass out the practice that we're going to work with today. Oh, Shadidra, you got lucky. You don't even have to move. Yes. So like, I mean, those sheets are literally, this is a review. Okay. All right. So let's look at the second one. So we had a lot of variability on the second one, that table that I created. Linear, tabular, exponential, table. I got a lot of tables, right? An exponential and table form. So table, is that a type of function? No, what is it? A representation, right? Graphical is a representation, tabular is a representation. It's a tabular representation. Type of function. Got a little bit more linears. We got some exponential in there. Any guess how I'm going to have to look at this to figure out what type of function it is? Say again. What do you mean?
Like, go to the graph and actually,
Say that one more time.
like, go to the graph and actually.
Oh, could you have graphed those points to figure out what type of function it is? Heck yeah. Let's look at that actually. That's interesting. That's an interesting point. So, what was that table? That table was -1 2/3, 0 2. 1 6 and 2 18. And I could have graphed it, right? You know what I get when I graph it? I get -1 2/3, 0 2, 1 6, and 2 18. So could we have graphed it?
Yes.
Heck yeah. It was the same exact function. And I did that on purpose because I want us to start to see that. You can see in the table, you can see it in the graph, they're going to tell us the same story. So, very clearly, just looking at it from there, it's what type of function? It's an exponential function. I will point out, though, what defines an exponential function? Because it's not just the graph, it's what? What makes it exponential? So it's a constant, multiplicative rate of change. One of the last things I left off with, I remember this detail. It's called a constant factor. So remember how a constant additive rate of change has what name? Constant additive rate of change is called a, saw it over here? I have it, but I don't have it named. That constant additive rate of change. Davian, let me ask you this. Repeated addition, how do we show that?
Repeated addition.
Yeah, how do we show repeated addition? What operation shows repeated addition? Okay, I need you to lock this in. I need you to write this down because we got to know this off the top of our head. Sarah, what shows repeated addition? Multiplication, right? Kyron, in this equation, what are we multiplying by?
The M.
The M. Okay, but I need better language than that. What is that M? That's just a letter. What is that M? What does that stand for?
Multiplication.
It might actually be where M comes from, but what is it? It's slope. Right? M equals change in Y divided by change in X. Right? M is, what again, Kyron?
Slope.
Slope. Can't forget that, right? The constant additive rate of change is called what? Slope. The constant multiplicative rate of change is called a constant. Because what do you do with factors, guys? You multiply factors, right? These names are not random. This is what I want you to understand. Like, this is one of the things I'm doing a lot of research right now on, is understanding the language behind mathematics and how if we can focus on the language, does it help it make sense, right? A constant factor, that's not random. What do we do with factors? We multiply. And constant, what does that mean? It just means that it's repeated. Oh my goodness, it stays the same. It's the same factors, the same multiplication over and over and over again. Any ideas what I'm multiplying by in that table? The exponential, the multiplication one. Say again? 3. So if I take 2 divided by 3 and I multiply by 3, what's 3 divided by 3? 1. So I'm left with what? What's 2 times 3? 6 times 3. So what's my constant factor? 3. Anybody know what, just throwing it out there, any guesses what, and this wasn't what I was assessing right here, but how would I write this equation? How would I write the equation for this function? There is something with 3 over 1-ish, but when you say 3 over 1, are you thinking because that's a slope idea? Like the change in y divided by the change in x? So be careful, change in y divided by change in x is the idea of slope, an additive rate of change. We are multiplying by 3, but there's something else with it that I'm missing.
3x plus 2.
So 3x plus 2. What do y'all think? Does that look like an exponential equation?
No, it's not like
It could not be. What's happening between 3 and x, guys? They are being multiplied, and multiplication, singular multiplication, is repeated addition. Guys, that's the equation of a line right there. Right? Y equals mx plus b. M is being multiplied by x. That's the equation of a line. Now, Landon, I got to ask, where did you get that 2 from?
y-intercept.
The y-intercept. Is the y-intercept still important? Yes, Mr. Kenny? 100%. But this time I'm starting at a 2 and then doing what to that 2? Multiplying by 3 repeatedly. So what am I still missing? I am missing an x, but where's that x supposed to go? So as an exponent on the 3. This is why we got to keep the type of function in mind and keep that rate of change in mind. This is not just, so we need to recognize, yes, we have a rate of change, we have a y-intercept, but what's actually happening, I'm starting at 2 and I've got a constant factor, so I'm going to multiply by 3. And Shadidra, how do I show repeated multiplication? Within, yes, I need a variable to show that it can change, but how do I show repeated multiplication? You're good? Hey, what's the name of this type of function? It's an exponential function? Because how do we show repeated multiplication? What is it, Shadidra? With an exponent. It's a variable, yes, but the variable just indicates that it can change. That exponent is repeated multiplication. I'm going to wait a second and let you take whatever notes you need to for your future forgetful self. That could be under tabular or graphical, whatever makes your heart happy. So keep in mind the difference between linear and exponential. They are very heavily connected, but they have a key difference. What is the key difference between linear and exponential? What tells us how the shape of the graph is going to look, what the table is going to look like, what the equation looks like. I mean, the x and y, the inputs and the outputs, but what tells us whether it's linear or exponential? What defines them? Constant additive and constant multiplicative. Linear has that constant additive rate of change that defines the table, it defines the graph, it defines the equation. Whereas an exponential has repeated or constant multiplicative rate of change. Right? By the way, don't forget, there's the side that has my solutions. Okay, just making sure. Oh, you ran out of space. Perfect. Okay, really quickly. Math Musician Monday, I just want to point out we're not doing that today because it's not Monday. Note about name cards. Mr. Hobby will be here for the rest of the year, Monday, Wednesday, Friday for the most part. So please make sure for the next couple weeks you get those name cards out for Mr. Hobby so that you can learn your names. I have a stack of people who forgot their name cards up here if you need one. I also have more paper up here if you need to grab a sheet of paper and make a new one before tomorrow. I wanted to show you something cool I found out about ChatGPT to help with math. I assume we know what ChatGPT is, whether we've used it or not. Seriously? So ChatGPT, it's an AI, artificial intelligence that was released over the last couple years. It's not really artificial intelligence, but it is machine learning. So let me show you this. This is even more exciting, mostly because I'm a giant nerd. So ChatGPT. Y'all remember that word problem that we did? The one about the pool and going to the pool the same number of times? Yes? So I entered, which is hard for you to see. I copied and pasted it over from something else, which is why it looks really weird. But I entered that story, right? Frank pays this amount of money every time he goes to the pool, etc. So I typed that into ChatGPT just to see what it would do. And so it gave me a very clear breakdown, right? Let the number of times Frank and Joe each went to the pool to be represented by X, right? Paying $25 per visit, etc. Notice it defined that 25X because it's repeated addition. $240 plus 10X. It showed setting those equations equal to each other, explaining it all the way through. So if you haven't ever used ChatGPT, I just want to point out it's not good for, copying down work because you're going to get to an assessment, it's going to be a struggle bus. But what could ChatGPT be really good for? Explaining things, right? Asking questions when you're not in the classroom. If you know the right questions to ask, it is really, really powerful. I will point out, right, so this is known as the vertex form of a quadratic. We'll get into that next week. And so it literally converted it for me. It explained how it converted it through, all the way through. And it actually did a really good job, right? I asked, can you convert it into factored form? And it told me why it couldn't. But it used the quadratic formula all the way through, right? So I want to point out this is a really powerful resource if you understand what is happening, okay? It works with imaginary numbers that we'll get into later. But here's what I really want to point out, okay? So I was just playing around with it yesterday. Again, really powerful. But I asked it to create quadratic functions. I'm actually probably going to use some of these later so that you have to identify these different features. And it kept giving me factored form, or it told me the vertex and standard form, but then factored form. Not easily factorable, not easily factorable. And it kept telling me that. So I said, hey, can you give me some that are easily factorable? And guess what? It did. Because I knew the right questions to ask. And it gave me an answer key for it, right? So be able to check these things. I bet if I went in and asked it to explain, it could. But, all right, can you now add some quadratics with irrational roots? Again, hopefully that makes you know that term, but it's possible you don't. But here's what I found out. I got to the end of the ones with irrational roots that it created. And ChatGPT is not infallible, meaning it can make mistakes. Right here, this function cannot exist. It would not work. Because what ChatGPT failed to recognize is that if this is one factor, this has to be the other factor. And so please be aware, it's machine learning. It can make mistakes. It can learn and grow from it, though. Literally, the next thing I did was I said, where to go? Here's my notes. I said, hey, ChatGPT, if a quadratic has an irrational root, then it must have a positive and a negative of that root, so functions 10 and 11 would not work. You could have this. That's absolutely right. By the way, be polite to the machines because when they take over one day, you want to be on the right side of it. But then they fixed 10 and 11 because I understood and could push back and clarify things. Your language matters and your ability to communicate matters. I could communicate with this machine, but also that means I can communicate it to a human being as well. So my point out of all this is, one, ChatGPT is a really powerful source. I had students last year in my AP Stats class who tried to use ChatGPT or some online AI to write a paper for them. It was really obvious and really bad, and so I talked about it later. So don't use ChatGPT to do your homework assignments, but use it as a way to check. Use it as a way to do research for you. Use it as a way to learn and to grow. It's just like online, you can search anything, right? There's another really powerful tool for that. But use it for learning purposes. Using it for cheating is just going to put you in a hole. So don't do that, but use it as a learning resource. All right, and if you haven't ever used ChatGPT, for real, really cool, really powerful stuff. It's the next side of, like, I know y'all didn't grow up with it, but like I grew up with the internet. Like, it was game changing. Once everyone had access to the internet, AI is that next version of the internet. So play around with it. It's really, really powerful. Moving from there, though, y'all need practice with what we've been doing. And we've been sitting way too long, and I did not intend that. One thing I want to point out, proficiency scale-wise, we have already covered if we can determine if a relation is a function or not. Identify the type of math representation. That's what I told y'all not to pack up earlier. We're about to move. But we're going to, actually, go ahead and move. We're going to move, and then you can get those things out. Because I know some of us did not listen and went ahead and pack. Can't do what he's talking about.
I just dropped off.
Yo, why you gotta do
already
that?
looking at
Calculator.
Gotta think.
Did you get the same one? Lucky you. Jane's like, I'm vibing. Hey Peyton, did you want a calculator, by the way? Oh, someone left there, so it's fine. Bella said we'll just switch. Actually, go ahead and take yours because you logged in. Thank you all for that seamless transition. I would, in the future, like to just be able to hand y'all a card and y'all go to the right spot. So let's try to make sure that's what happens so I don't have to change things up. But relations, functions, mathematical representations, we have covered everything off the foundation there. It's also on one of the Check Your Understanding and Notes pages. Now, this one here, given any mathematical representation, graph, table, etc., determine if a relation is linear, exponential, quadratic, or none of these. Have we covered all of that yet? No. We'll get into quadratics tomorrow. Okay? Determine if two relations or functions are equivalent and explain why they're equivalent. Have we talked about that a little bit?
Yeah.
Yes. What makes them equivalent? If what? I mean, because like the table and the graph earlier were equivalent, right? Why were they equivalent?
Had the same. No,
Not just same rate of change.
not the same. I don't know the word for it.
Starts with an I.
Yes, sir.
Tell me this. What is this input and output? Input is,
Two. Or is it two?
what's the input?
Oh, no. One. Maybe one.
This one?
Zero.
0. What's the output? 2. What's this input? 1. Right? Output?
Six.
What's this input?
Maybe one.
Negative 1's the input. What's the output?
2/3.
2/3. So the same inputs are mapping to the Same outputs. That's what makes it equivalent. Remember the way I've said it before was, they look different, but what? Tell the same story. I think it was Peyton earlier who said, hey, could I have graphed that table? The answer was yes, right? They look different, they tell the same story, right? Same inputs mapping to the same outputs. That's the idea of determining if they're equivalent. You can do it multiple ways. So linear, exponential, equivalent, but we just haven't covered quadratic yet. We will soon. And in this one, functions with constant rates of change. Hope, tell me what type of functions have constant rate of change? Which types of functions have constant rates of change?
I don't know.
You don't know?
I don't know.
You literally said them earlier. Davis,
What did you say?
what types of functions have constant rates of change?
Linear?
Linear has a constant,
Rate of change?
say again?
Rate of change?
Yeah, but what type of constant?
I don't know.
Linear. Let's see, Brianna, haven't called on you at all this morning. Linear, constant what rate of change? Additive, right? Remember, linear at constant additive, right? That's a constant rate of change. Okay? Mary, exponential, constant. Remember, it's called exponential for a reason, because what's an exponent? Repeated,
Multiplication.
right? An exponent is repeated multiplication. So an exponential function has a constant multiplicative rate of, right? Constantly adding the same amount or constantly multiplying by the same amount, constant rate of change. So we have all these terms here, and determining slope, constant factor, that's what we're about to get practice with. But this is what we have covered, now it's time for practice. That's why you're in these groups. So, I want us to take, let's say, 7 minutes for numbers 1 through 3. Please notice, I am telling you that we have 3 functions, and I have already given you the equations. I need you to explain why is this equation correct based on this graph? Why is this equation correct based on this table? So these equations are correct. I need you to find out why those equations are correct. Okay? Why is this a 6? Why is this a 1/3? Why is this a -12? Why is this a 3/4? So 7 minutes, let's get up to our vertical surfaces and let's start working on that. Actively collaborate, talk, help each other grow and learn. So looking at the board, I want to emphasize and remind you to use these different equations and the graphs to help you think through things, but also how easy was it writing the equation from the graph for this very first one? Anyone have an easy time writing the equation from the graph?
Yeah.
Yeah? I wouldn't have. What's the best representation for finding patterns, guys? A table, right? If I'm trying to write an equation, especially for what type of function would this be? Exponential, right? If I'm trying to write the equation for an exponential, I'm for sure looking at a table. And it's 18 times 1/3. 6 times 1/3. And so why is there a 6 right here? I know we found it, but that's the what? Y-intercept. Why is it a 1/3? Because that's my constant rate of change, but be careful. You'll never hear me just say constant rate of change, because how many rates of change, constant rates of change are there? There's 2. So which constant rate of change? Constant what? So constant multiplicative, but what's the name for it?
Factor.
I want us to keep in mind, right? Connect those two ideas. Those two words, or those two phrases are telling the same story, right? Constant multiplicative, rates of change are constant factors. That's where the times 1/3 came from. How many of us got freaked out by that -12 in number 2 to start? Sarah's like, I did. I heard it from this group, right? We're looking at it like, Mr. Kinney. I heard someone actually ask, Mr. Kinney, shouldn't it be 12? Why is it not 12? Is that what you were thinking it was, Hope?
I don't know.
You don't know why it's not 12? Say again. Remember, for a y-intercept, my input has to be
Oh.
0, right? For a y-intercept, my input has to be 0. Is that an input of 0?
No.
No, so what did this group do? They kept it going. -8, -8, -8 until they got an input of what? 0. And so when they subtract 8 from x, they have to subtract 6 from y. Oh, there's -12, right? All right. And so we see, how do they calculate this 3/4? Because I don't see a 3/4 anywhere on here. Where do they get 3/4 from? Slope, how do we calculate it?
Triangle, I don't know. Like triangle, wild triangle.
You can just call it change in y and change in x, right? Delta is the Greek letter, but you can do y2 minus y1 divided by x2 minus x1. But remember, that literally just means change in y. This literally just means change in x. This is the form I go with because it's simpler. If you want to go with this one, go for it. It's your choice. But how much is my y changing by? -6x. -8 and -6 divided by -8, so be careful. Right? It's change in y divided by change in x. I should have caught this. -6 divided by -8 is what? And so again, also be careful here. It looks like they're making x an exponent. But should x be an exponent if we're constantly adding?
No.
No, remember, an exponent is repeated what? Multiplication. We're not multiplying. That's why it's -12 plus 3/4 times x. And I think number 3 was probably a little bit easier, hopefully. One note that I do want to make just looking here and being careful about this. If I take 3 and I divide it by 4, that's a positive 3/4. Why in the world is this negative?
Because you're going down.
It's going down 3, right? Down 3 and to the right 4, which is positive. Be careful with your notation on those things. So, if you want to take a seat for a second, write down some information there, or write it on your, check your understanding in Frere models. Go for it. We're going to pick up with the next section in just a minute. While we're doing that, come around, please ask questions if you need them. That's a great question. Let me remind to talk about that. The reason why I use F, H, and K, it can literally be anything, but it's naming it different functions. So the reason why I did F here, H here, and K here is to indicate that those are 3 different functions. That is function K. Like the X is my input, so it has to be. Correct. Whatever my input is, that needs to be my input. Yeah. So be careful, and what matters is that we stay consistent. So if you're doing 24 minus 6 is 18, then you have to do 48 minus 8 is 40. Right? Because if you do -6 divided by positive, you get -3/4. If you want to do the plus 8, you have to go up. 0 plus 6 is 6. 6 plus 6 is 4. The reason why the minus makes so much sense, I would say, in this one, because I will say going up is the correct actually in this one, but the reason we want to go down is to get to that input of 0. Does that make sense? So you have to be careful about that. I'm glad you asked that question. But do note, regardless, that is not my y. That's the x, right? There's my y. And then be careful of those negatives. That's what this is coming from. So it's y and then x. Because also remember, the first way you ever learn slope was rise, is in that y direction, and then the wrong way is in x direction. understanding, right? To practice it. We good? Questions? Any questions? I can answer. So keep in mind, one of the things I will point out is, just because this was thrown off a little bit earlier, just when I was hearing this conversation, identify what type of function it is first. So that's going to tell you what equation to use or what features to look at. Okay. Any questions? You don't know if you have questions? Okay. I'm going to come over and check with y'all when I get everything started on the next piece. Okay. How y'all doing? You don't know? Okay. Keep thinking on it, let me know. How you doing over here? Okay? Just okay? Questions that you know you have yet? Yeah. Any other years? Yeah. It's good, it'll come back. That's why we're doing some practice with it. Be careful though, notice you have the same issue right here. It should be -6 divided by -8 divided by 6. It's y divided by x. All right, while a couple people are finishing up their last bit of notes, two things I want to talk about because this is a great question that I had from two different people. One, I do want you to note f of x, h of x, k of x. You can use whatever function notation you want. I used f, h, and k because these are three different functions. Could have called it m of x, n of x. It just names the function, right? So this is function f, this is function h, this is function k. And you can use whatever input you want to just be aware on a graph. We have x and we have y. One final thing I do want to point out because it's going to help you later. Also notice, like if I substitute a 1 in, what did that 1 just take the place of? X, right? So what's going to take the place of this x? 1? And anyone know what 6 times 1/3 will come out as? 2. Because the input of 1 maps to what output? 2. That does not change. Whether it's a graph, a table, or an equation, the same inputs map to the same outputs. Miles, what's that called when the same inputs are mapping to the same outputs? Remember, it's 3 different representations. They look different, but they're telling the same story. There's an E word. The one I asked you about earlier. Huh?
Equivalent?
Equivalent, right? Same inputs are mapping to the same outputs. Same thing over here. Now, I will point this out. If I'm making a table and trying to make my life easy, would it make sense to substitute a 1 in for this x? Will that make my life easy? You could do it, but that give me -3/4 plus 9. Is that easy? Do you like dealing with fractions? Miles said, no, Mr. Kennedy, that sounds terrible. Does anyone know what a good input right here would be? To make it easy to simplify? What about a 4? Or maybe an 8? Or what about a -4? Where am I getting those numbers from? So pay attention to what we're dealing with. Greg, read this number for me real quick. What is this number? Say that last bit again.
3 divided by 4.
Because we're dividing by 4, what kind of inputs am I using? Using multiples of 4. Doesn't that make the division easy? Just something to keep in mind. Over here, same thing, I would use multiples of 4 because it's dividing by 4. Last detail, and then we only have 5 minutes at that point, so I'm going to have y'all just work at your groups for a little bit. Keep in mind, rise, that's the first way you ever did slope, was rise divided by run. Peyton, if things are rising, what type, is that an X or a Y idea? Huh? That's y, right? So rise is the change in y. Run, change in x, right? Rise, y, x is run. So keep that in mind. With these last few minutes, I do want you to go ahead and start on 4 through 6. Just chilling at your group, talking about it, practicing these ideas. We'll practice some more tomorrow. Be aware we will have a check your understanding on these ideas at the end of class tomorrow, so we'll get some more practice in class before I ask you to put it on your own. You got this. You're doing it.
Huh?